I'm Daniel Langdon, and this is my data structure-oriented introduction to Git and GitHub. Now, before you even ask, I know there are a million presentations and books and tutorials about Git. And there's one thing that I think a lot of them get wrong, and that is illustrated very well by Randall Munroe here in XKCD. Um, Most of these tutorials, will explain Git by giving a list of commands for common operations and say, this is the command you do for this operation, this is the command you do for that operation. And as long as your scenario is exactly like what they show in the book, then it works. But as soon as it's a little bit different, you start having problems, and then you end up doing things like Qball here is doing an XKCD. He says, "Oh, how do I use it?" Well, you just use these shell commands and type them to sync up your work. And if you get errors, save your work elsewhere, delete the project, and download a fresh copy. That's something I've done many, many times myself, but never again, because I'm finally getting a handle on this, and I'd like to share with you how I came to understand Git. I mean, like I said before, there's a million books and tutorials about Git. But I would like to share with you how I came to understand it, in the hopes that it'll make it a little bit easier for you. So if you've ever deleted your copy of a Git repo and recloned it because you didn't know what Git was doing, or if you've ever made a copy of your data outside of Git, because you feared using the wrong command and destroying your data and not being able to get it back, then this is for you. Git was actually created by Linus Torvalds, also the creator of Linux, and he said, bad programmers worry about the code, good programmers worry about data structures and their relationships. Under the hood, Git has a whole lot going on with its data structures, no doubt. So what I'm going to be giving you today is like a 10,000 foot view, where you're going to see, the basics of these data structures and how they work together. So all that being said, there's a data structure fundamental to Git, which is probably going to look familiar to you. The simplest Git repo resembles a stack. When a new value is pushed onto a stack, a node is created to hold it. When a value is removed, its node gets removed. And I have here some very simple JavaScript code to implement a stack. This is, of course, not how Git works. I'm doing this for illustrative purposes because this is like what Git does. So each incremental change in a Git repo is called a commit. And here's what's really important for you to know about a commit. A commit contains the contents of every file that was changed in that commit, as well as who created the commit and when it was created. And that's used for tracking purposes. As you make these incremental changes, you have all these commits that you go through, and those commits give you the entire history of the project. The commit is the fundamental data structure used in Git. And before we start talking about multiple branches and whatnot, when you have a Git repo with a single branch, it's just like a stack. You traverse the stack from top to bottom, and you get the history of the whole repo. So here's a simple example I'm going to work with. Let's suppose, we have a man named Ernie who's writing the documentation for a project in English. And then we have Sammy and Frank doing the Spanish and French. And if we think of each of these as being in its own commit, we can think of pushing them onto a stack in JavaScript. And like I said, Git is not a JavaScript project, but this is very similar to what Git does, and I believe that thinking about it this way will help you conceptualize it. But how it actually works is yes, it's like a stack, but a stack resides in memory, and each node in a stack, by convention, is an object reference in JavaScript, which is really just a fancy way of saying it's a managed pointer. And since Git is a utility that manages your work on the hard drive, I mean, you don't have a specific location in physical memory. So the way Git refers to these different commits is each one has a hash of its contents computed, and that becomes the ID of the commit. Is it possible for two Git commits to have the same ID or the same hash? Absolutely. But we're likely to see the heat death of the universe before that happens. So to get started with Git, now that I've talked a little bit about the data structures, let's talk about some of the basic commands to manipulate them. See, there's over 100 commands in Git with many parameters, but you can do 99% of the work with just a handful of them. And failing that, you've got Google and Stack Overflow out there to help you. Just keep in mind, as I said before, I want you to do your best to understand how these data structures are organized, because if you understand the basics of the data structures, the commands are pretty intuitive when you read the documentation. But if you're just looking at a list of commands and you don't understand what a commit is, the commands may as well be Chinese. So we'll start with these three commands: init, add, and commit. Init creates a new blank Git repo, and git add will add files to what we call the index, which is simply means the files that will be contained in a newly created commit. And finally, we have git commit, which is the command that actually creates the commit. You can think of the index as being like a ghost, that becomes a real commit, when you type the git commit command. So going back to the example of the English, Spanish, and French being done in 3 commits, here's what the shell commands actually look like. You see, you do a git init to create a new repository, and then you do git add english.txt, git commit, and then you can add a comment, git add Spanish text, git commit, and then a comment, git add French.txt, then add a comment here as well. And I think you're probably wondering, oh, what are all these letters and numbers inside the bracket here? Well, this is just something that the Git shell will show on the screen as to help you follow along with what it's doing. Master here is the name of the branch that you're currently working on, and we haven't talked about multiple branches yet, but when you create a new repo, you get one branch. It's called master. We'll come back to that later. The red numbers stand for files that are in your working directory that haven't been committed nor added to the index. Green numbers stand for files that have been added to the index but not yet committed. So at the beginning, we have English, Spanish, and French. So we have 3 files. See, the plus here means these are 3 files added. The tilde means changed, and the minus means deleted. So once we add that to the index, here we have 1 file in the index and 2 that are outside the index. And then after we commit that, then we only have 2 files, and so on and so forth. So here I have a plot of the graph of commits that I created with a handy little utility called gitk. So here you can see how this is in a stack structure where you have French documentation as the last commit, and then the parent commits going back to the beginning are the Spanish and English. So this is about the simplest Git repo you can possibly imagine. So we're just going to build off of this. So when you use Git or TFS or SVN, one of the primary reasons for using that tool is you want to be able to go back. You want to see, well, what was the project like yesterday, or who was the last person to do something? And Git provides all kinds of stuff for this. So let's give an example. Suppose that Sammy turned out to be an incompetent writer, and we want to fire him and get rid of everything he did in our repo. So let's get rid of that Spanish documentation. Git provides us 3 very handy commands for reverting the repo to a previous state. We have checkout, revert, and reset. checkout moves the head pointer back to a previous commit in order to temporarily go back. That basically means we change the contents of our working directory to something that they were in the past, and I'll explain more on how that works later. Get revert creates a commit that does the reverse of a given commit. So in this example, we can revert Sammy's insertion of Spanish text by doing a get revert on that commit, which will create a new commit that deletes the file. And that way we preserve our ability to go back and see what we did, if that's what we need to do. And then finally, we have get reset, which can move the branch pointer and the head pointer back to a previous commit. And the important thing to note here is if you move the branch pointer back, then you can disconnect one or more commits from the graph, and then they can eventually be garbage collected and lost forever. So that's a really important thing to know about get reset, and get reset is something you always want to be careful with for that reason. So what's a branch pointer? What's a head pointer? I'm going to explain that in a little more detail shortly. And finally, I want to point out get log, because checkout, revert, and reset all require that you specify the hash of a commit that you want to go back to. And get log gives you the history of the repo, shows the hash of each commit. And so you need that command in order to know the hash of the commits you want to go back to. So here's a worked example with get revert. So we're going to undo what Sammy did. So first we do get log, and here we have the hash. It's a 40-character hash of each commit. So here's the one for French, and here's the one for Spanish. And mercifully, get allows us to use the first 7 characters of a get hash, so long as that makes it unique. So here, in order to revert this, we type get revert, and then the first 7 characters of that. And here it says it's adding a new commit. And when we do get k, once again, we can see there are now 4 commits, and it says here that this 4th commit simply reverted the commit that added the Spanish documentation. So what's a head pointer anyways? So I mentioned that the checkout command moves the head pointer, and reset moves the branch pointer and the head pointer, but I didn't tell you what that means. So when you're working in a Git repo, we think about it as being a graph of commits. And the head pointer simply points to the last commit you are working on in your working directory. So using the stack analogy, as you have a repo with a single branch and you add more and more commits to it, the head pointer is continuously pointing to the top of that stack. And then the branch pointer, well, this is where we break that stack analogy, because one of the main features of Git is you can have as many branches as you want. So a branch pointer simply represents a commit that represents the tip of a branch. So what we can do is we can break that stack up into a tree structure and then have a branch pointer pointing to the end of each branch. So by default, as I pointed out before, there's one branch. It's called master. And the Git repo with one branch is like a stack, and we make it like a tree when we add branches. But don't worry, we'll break this nice tree analogy too. So in order to illustrate how branching works, let's give Ernie and Frank new tasks. Let's say that Ernie has been told to create separate documentation for British English and American English, and Frank has been asked to correct punctuation errors in the French documentation. So let's go ahead and create some branches, and I promise I will return in due time to how to use the get reset command. Branches can be created, deleted, and listed using the get branch command. You can list the branches, create a branch, or delete a branch as shown here. So let's go to Ernie. So Ernie's now going to create a new branch to keep this work he's doing separate from Frank's work. He's going to create an American English file and a British English file, and then delete, the old English file. And once this is all done, the boss is going to add Ernie's work to the master branch. So the first thing he does is he creates a new branch, and he's going to call it dialects. And then he moves the head pointer to dialects with the checkout command. So now the working directory is on the dialects branch. He makes his changes and then creates a commit. And we're going to look at the resulting graph with GetK that now has a master branch and a dialects branch. But first, let's check in on Frank. Just like Ernie, Frank is going to create a new branch for his work, and he's going to call that branch punctuation. And I know this is kind of a contrived example, but let's suppose that Frank does work today to fix sentence ending punctuation, and he commits that to the punctuation branch. And tomorrow he does work to fix misplaced commas, and then he does another commit for that. So Ernie did one commit, Frank did two commits, each on their own branch. So let's look at the graph once again with GetK. So now we can see three branches. Each one is highlighted in green. So the master branch is back at revert added Spanish documentation, as we talked about before. We have a dialects branch with a commit that says divide English into two dialects. And then we have a punctuation branch that contains two more commits, one for sentence ending punctuation and the other for commas. So now we've broken our beautiful stack into a tree-like structure. So in order for us to continue and give Ernie and Frank more tasks, the bosses and the QA team are going to review this, and then the boss is going to merge Ernie and Frank's work onto the master branch. Because we don't want them to just keep splitting up and making more and more branches, because then we'd never be able to keep track of them all. But before the boss can merge Frank's work back into the master branch, he realizes there's a problem. Frank was given a task, and company policy dictates that each task shall have one and exactly one commit to represent changes for that task. So Frank's doing his work in two commits violates that policy, and Frank needs to fix that before we can continue. So let's see how Frank gets into compliance. And this is where I'm going to give a worked example of using the reset command. Please pay careful attention here, because the reset command is dangerous. If you're not sure what you're doing with reset, there's Google and Stack Overflow. There's plenty of help out there. So, please reach out for a hand, and don't take a chance that you're going to lose your data. So the basic use of get reset is to move the branch pointer and the head pointer to the commit that you specify. And the point here is this can leave one or more commits inaccessible from any branch. They can be disconnected from the graph once you move that branch pointer back. And you can optionally reset the contents of your working directory to the contents of the new commit that you move the pointer to by using the hard parameter. We call that a hard reset. Otherwise, it's called a soft reset. And another little shortcut I'd like to introduce you to is that thus far I've always referred to commits by the first 7 characters of the hash. However, Git provides a convention that you can refer to in commits back by head tilde in. So that can be convenient, that you can save yourself, the trouble of looking up the hash when you simply know how many commits back you want to go. And also you should know there's another command called reflog, which will allow you to see commits that are no longer accessible from any branch, that are disconnected from the graph. And that can be used to prevent data loss by moving the head pointer or the branch pointer back to one of these orphan commits as you like, but beware, they'll eventually be garbage collected by Git. So don't just assume that you can always go back and get them. If you realize that you've disconnected a commit you need from the graph, go back and get it immediately. So in short, yes, get reset is a dangerous command, but when you understand what's going on and you know how to use the commands, the damage can usually be mitigated. So be careful, Frank. Git reset is dangerous, and Frank needs to use git reset. And his task is very simple. He's simply going to go back 2 commits and then replace them with a new commit. And in order to guard against data loss, Frank is going to create a new branch called punctuation2, and he's going to use git checkout to move the head pointer to it. So this is an extra redundant step to take to make sure that Frank doesn't do the wrong thing with git reset. So I mentioned git reflog before as a way of possibly being able to see commits that have been isolated or disconnected from the graph or the tree or whatever we want to call it. And by creating a new branch and working with the new branch, he keeps the old commits on the old branch. So that adds another layer of redundancy to prevent Frank from losing data, which is really handy in more complicated scenarios. So Frank is going to use on punctuation2 git reset head tilde2, and that will move the head pointer back 2 commits. That will move the branch pointer back 2 commits. So those commits are no longer on the punctuation2 branch. However, the contents of those commits remain in Frank's working directory, so he can then create a new commit, and he sends that into the boss for review. So I've shown the shell commands below, say git branch punctuation2, git checkout punctuation2. Frank has now created the branch punctuation2 and changed to it. It says git reset head tilde2. Notice that the red number appears again for French.txt because the change he made is no longer part of any commit. So he does the git add and the git commit, and now punctuation2 is a branch that contains Frank's work on that task in a single commit as the boss ordered. So now the boss has his work cut out for him. He has his people review the work done by Ernie and Frank. Everything looks great. So he wants to move all this back into the master branch before any more tasks are done. And there's 2 primary ways of doing this, each having its advantage and disadvantage. And once again, this is a very simple example, and there are lots of ways that this can be complicated. And I want to make sure that you get the basics here. And when you get into one of the more complicated situations, you have some background to build on when you understand how to accomplish what you need to. So the 2 commands here are merge and rebase. Merge commits from 2 branches together. So this has the advantage of often being the easier operation when many commits are involved, because it simply creates a new commit that is the result of merging the top commit from 2 different branches together. And the disadvantage, though, is that you've now broken the tree structure because you had 2 branches that came apart and then go back together. Now, if you have conflicts between those branches, Git is going to prompt you to resolve those conflicts by taking the change from one branch or the other, and there are a number of tools out there for doing this. Git rebase applies commits from one branch on top of commits from another branch, and this has the advantage that it avoids, forking and putting the master branch back together. But the issue here is that those commits are merged from one branch back onto the master branch one at a time, and depending on how you have conflicts, you can have to resolve conflicts every step of the way. So it really just depends on your requirements and your specific situation. So here I am going to illustrate how the boss could do this task with either command. So once again, this is where having some understanding of what a commit is, how they're related together, can make it a lot easier to understand how to do what you have to do. So let's do git merge first. And once again, this is where I keep my promise to break not only the stack structure, but the tree structure as well. So git merge, as I said before, simply creates a new commit by combining two branches, and the resulting commit has two parent commits. So looking at the graph in git k here, I forgot to mention, we did go ahead and delete the punctuation 2, and dialects branches once the merge was completed because we don't need them anymore. So now we're back to having only one branch called master. And if you see how it goes back to the beginning, we have English, Spanish, French, and then we removed Spanish, and then we branched. We had divide English into two dialects and fix French punctuation, and then we merged them back together into a single commit at the head of the master branch. Now let's do the same thing with git rebase. So as you can see here in the git k diagram, we've preserved that stack structure for the master branch. We have all of our commits here in order with the last two commits on top. So with git rebase, the commits from punctuation 2 and dialects are applied back to the master branch, and then the old branches can be deleted. So we take what's in punctuation 2 and we apply that to the master branch. We take what's in dialects and we apply that to the master branch, and that's done in separate operations. And once again, we made this simple by having one commit in punctuation 2 and one commit in dialects. But if we had say 10 commits in dialects, which in a real world example we possibly would, we might possibly have to resolve conflicts with every single commit, and that would not be fun. So in review, thus far we have discussed how Git stores your data and its history, and the commands I've introduced so far include init, add, commit, checkout, revert, reset, log, branch, merge, and rebase. So these are the basic commands for working with branches and commits. Now, I want to point out that we worked an example of several people working together on different tasks in a single repo, but this is typically not how it works. Typically, we're using a collaborative, distributed collection of repos using a tool such as GitHub, which I will get to in part 2. And rather than having several people working on a single Git repo, what typically happens is each person has their own copy of the repo, and each person does their work on their copy, and then they have to merge across multiple versions of the different repo back to a master copy. And that is what I'm going to talk about in part 2.